So we heated a filament, and you should understand the details of this. The filament is a conductor. It has free electrons. And this is a part of physics we don't really cover, thermodynamics. But when you heat things up, temperature, there's a direct correlation between temperature and the kinetic energy of the atoms and molecules in the water or the electrons in the wire. So temperature is a measure of the average kinetic energy. So as the temperature goes up, the kinetic energy goes up. And as the kinetic energy goes up, the velocity goes up. And as the velocity goes up, they eventually move fast enough that they pop off the wire. And that's what happens when you boil water, right? There are water molecules that are moving around in the water, and it's proportional. I'll give you a little bit of thermal here. It's proportional to the temperature in Kelvin. So this is 300 Kelvin. Those water molecules are actually moving quite fast, but as you heat them up to 373 degrees Kelvin, 100 degrees Celsius, now they're moving so fast that they pop out. And they leave as a gas. So it's that sense in which we use the word boil, because it's similar to boiling water. You drive the water molecules out of the liquid. Here you drive the free electrons off the filament by getting them to a high enough temperature. But some of you got confused. Once we set this, and you saw the current in the filament went up and then went back. That was one of the questions, and that's because the filament, when it's cold, has a low resistance, right? You answered that question. And so it gets hot and it gets stable, and we never touched that. We never adjusted that. So we have this hot filament boiling electrons off in all directions, not in one direction. In all directions, the electrons are popping off, and some of them get between the two plates where we control the voltage between the plates. And so they go across. And all the electrons go up, and most of them are going to hit the upper plate, but those that hit the hole go through. And as we dial the voltage up, we increase the velocity. So the beam got brighter, not so much because there were more electrons, but they were moving faster, and they're fluorescing the gas more, right? So that's a detail that we didn't get into, but the fluorescence is a result of how much energy they have. And if they have more energy, they're causing more fluorescence, and you see it brighter.
Wouldn't that be like work?
Well, there's two ways of looking at this. Yeah, this is doing work and changing kinetic energy. But a better way of looking at it is we're taking electric potential energy and we're making it kinetic energy. So the change, this is the equation that you should have used, that the change in electric potential energy, which is the result of the charge and the voltage difference, equals the change in kinetic energy, assuming they start with very little kinetic energy, which may not be right, but we just do that. Then the velocity and the voltage are directly related. Well, related through the square. So you should have written this equation down. Now, you can also think of it as there's an electric field, and the electric field causes the electrons to accelerate and come out the hole. And that's a perfectly valid way of doing it, but the mathematics is a little more complicated to come up with this relationship using force and acceleration. It's just much easier to get at it through the energy. And so this was the equation that explains why, as you increase the voltage, you increase the velocity. And the equation that we used a lot was, okay, so now you have these electrons, and you're going to bend them into a circle with a magnetic field. And the equation that gets us there, it's actually the first equation if you look at the lab sheet, is that we exert a force on the electrons such that they bend according to this equation. Right? That's, you have a field and a velocity and a charge, and they're going to bend, and the sign is 1 because it's perpendicular according to ma. So the force on the electrons results in an acceleration, and since it's circular, that acceleration is v squared over r. So we use this equation many, many times for many situations, right? And one of the b's cancels. And in this case, we want to know Q over M, the charge over the mass. And so Q over M means is going to be equal to V over R. And the whole thing would be very simple if we could just measure VB and R. And could we measure V? You could. If you had a magnetic field measuring thing and you put it right in the middle of the coils, you could just measure it. But we don't. So how do we get B? Well, there's that rather complicated equation for B that I didn't expect you to remember. But what you should know is to get B, what did we measure? We measured N, we measured R, we measured S, and we measured 4 things to get B. So that's what you were supposed to have listed in part F. The number of windings in the coil, the radius of the coils, the separation between the coils, and the current in the coils. That gives us B. What's this R? This is this radius, right? The radius of the circle that it bends in. So we did measure that directly by looking at the rings. And the last thing is V. So some of you said, oh, you need to, these are the things you need to get Q over M. You're right. Those are the things you need to get Q over M, but these two you can't measure. So you measure these to get B, and what do you measure to get the velocity? You measure the voltage. So the volts across the plate. So you measured this, you measured these 4 things, and you measured the plate voltage. There were 6 things that you measured. So what's nice about this experiment is it ties a lot of the physics we know all together. Okay. Let's, so no questions on the assignment?